first talk about inferential statistics and how we've used them so far. And you've been doing inferential statistics since we started z-test. So z-tests are a part of the inferential statistics. Also t-tests are one sample and two sample, independent or dependent, and also ANOVA, so when we did an f-test. So all these are inferential statistics. And what we did was we wanted to know something about our population. Let's say we want to know something about the United States here. And what we've done so far is we wanted to know about something about mu, which is our population mean. Or we might have a few populations and we want to compare those populations. So what we do is, because we can't survey the whole United States, or maybe we have other countries we want to look at and we say we want to compare the different countries, we can't go to each country and survey every person in the whole country. So what we do is take a more reasonable, what we call a sampling frame, which is the people that we have access to, that we can talk to. And even that frame might be too big. It might take too much time to sample everyone. So we take a small sample. So we sample from the sampling frame, and then we get data from them, and then we calculate sample means. And we use the sample mean to make an inference about the population here. So we take the sample mean and we try to make an inference about the population mean. So what we're doing is using sample data to make this kind of educated guess about our population of interest. So that's basically what inferential statistics is, and we can use these Z, T, or F tests to help us make this educated guess. It helps us make this decision about the population with only sample data. So just keep that in mind. And when we do inferential statistics with a T or a F, say we have three categories, so in this case we would do a ANOVA because we have three categories. Or the same thing goes for a t-test. What we want to know is there a difference between the sample mean? So the mean for category 1 is about 4.4 or so. For category 2 here it's 2.5. And for category 3 it's 3.5. So here's the means, and we want to know are these differences. So this is the difference between 1 and 2, and then the difference between 1 and 3 here, and then the difference between 2 and 3. So ANOVA tells you is one of these, at least one of these differences significant. And how you determine if, so say we had these three categories. So category 2 had a mean of 2.5. So let's put the mean here, say it's 2.5. And then category 3 had a mean of about 3.5. And category 1 had a mean about 4.5. or 4.4. Okay, and what we want to know is if the difference between these dots, or different enough if the difference is big enough to say it is more than just chance. So, we took a sample, right? And each time we take a sample, the sample's a little bit different. So it could just be that these differences are occurring because of random chance, that, we don't have the whole population. So the sample means could vary from the population means just by chance. So each time we take a sample, the means might just be a little bit different. So say the population means for each of these categories are really 3, maybe it's just that we got 2.5, 3.5, and 4.4 just by chance. But we have to compare this to the variability within each group. So this distance from here to here, and the distance from, here to here, and from here to here, this is like the standard error or the mean square error, or within, depending on what test you're doing. But this is the bottom, the denominator of your statistic. So when we have ANOVA, do an F, and then you have between versus within. And the bottom is the within, the distance within each group. And the between is the distance between the means, okay? So there's 3 things that go into it to see if this is significant. If we can say this is different enough to say it's just more than chance. So one thing is the between. So to say if it's significant or not, it's based on basically 3 things. The between variance, or the between the sample means, the within variance, or the standard error if you're doing a t-test. This is the same kind of concept. And 3, the sample sizes, or the sample. So they're n's. So you're more sure, right, if you have a higher sample. It's more likely that this could be due to just chance, and you're not really as sure if the sample size is too low. If you have 100 in each category, you're more sure of your means than if you only had 5 in each category. So those 3 things, what you consider when you're trying to do inferential statistics. And before, we're just comparing the means. And also, our predictor variable, or our independent variable. So make sure you review what these are if you don't remember. This was in phase 1. That would be a nominal variable. So things like gender, race, these are categories. This is these are categories. And our outcome was scale. And outcome, or also the dependent variable. And that was a scale variable. So something you can average. It's numerical. So like age or income. Some good examples. Okay, so this was for t-test or ANOVA. either one, we're comparing means, sample means, and just the ANOVA is when we have 3 or more, and T is 2 or 1. So now we're going to go on to correlations. How do we do this with correlations, and why do we need to do it with correlation? So when we do a correlation, we have 2 scale variables. So both are independent and dependent variable, or a predictor and outcome variable, are both scale. And let's take this for example. So we have 2 examples here. One, we have 3 dots. So our n is 3, and then our n over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, 13. So both are positive relationships, but they're both sample data. So which one would you be more sure that in the actual population we have a correlation? Well, I hope you would say this one, because our sample size is higher. So maybe these 3 dots were just, just random, and they just happened to look like a pattern. But, if you just moved 1 dot somewhere else, then it wouldn't have looked so much like a pattern. But with it n equals 3, if that was all due to chance, it's a pretty strong correlation. I mean, you just got really lucky or unlucky, if you want to call it. So you also want to consider sample size when you're doing correlations, but also the strength. So we can have 2 things with the same sample size. So both these have n equals 6, but this one's stronger. Correlation would be stronger than this one over here that's more spread out. So I would say the one that I circled is probably going to be more likely to be significant than the one with a weaker correlation. So the same things you want to consider with correlations and inferential statistics. It's just a little bit different. So you want to consider the strength and then, so that's instead of the difference between the sample means, instead you want to consider the strength of the correlation. 2, you still want to consider the within variance. And 3, you still want to consider the sample size. So the only difference is now that we have 2 scale variables, you can't, put a mean for each group because there's no groups anymore. So instead we do a correlation, and instead of the difference between the means, now we're doing the strength of the correlation that determines if this is significant and if it's due to more than just chance. How likely is this due to chance versus there's actually a correlation.